Picture a place of absolute silence and endless night, where temperatures plunge to nearly 400 degrees below 0 Fahrenheit, a cold so profound it defies imagination. These are the Moon's shadow zones, mysterious craters huddled near the lunar poles where sunlight has never reached, not once in billions of years. They are among the coldest known places in our entire solar system, and they hold a secret that could change the future of human knowledge. In these deep freezes, far from the turbulence of our world, we might just build the ultimate sanctuary for our most precious digital treasures, a library not of books, but of bytes, designed to last for millennia. Here on Earth, we're creating more data than ever before in human history, from scientific breakthroughs and cultural masterpieces to personal memories and global records. Yet all of it is vulnerable. Natural disasters, rising oceans, cyber attacks, or even simple decay threaten to erase what we've worked so hard to build. We store our collective legacy on hard drives that fail, in data centers that consume immense energy, and on media that may not survive the centuries ahead. It's a silent crisis unfolding in the background of our digital lives, one that asks a profound question: how do we ensure that the story of humanity isn't lost? That's where the Moon's shadow zones come in. These natural vaults offer something we simply can't find on Earth: a perfect preservation. In this video, we'll explore how these eerie, dark basins could become the guardians of our digital future, protecting everything from irreplaceable research to the languages, art, and stories that define us. We'll journey from the pressing challenges we face today to the breathtaking possibilities waiting at our celestial doorstep. This isn't just about technology, it's about legacy. It's about ensuring that whatever happens on Earth, a part of us endures. So come with us as we uncover how humanity might turn the Moon's darkest corners into a beacon of hope for generations to come. To truly grasp why these shadowy lunar basins are so special, we need to venture to the Moon's poles. Unlike Earth, which has a significant tilt that gives us seasons and spreads sunlight fairly evenly, the Moon is only tilted about 1.5 degrees on its axis. This means its polar regions are topographically unique. They contain deep, ancient craters whose high rims act like permanent barriers, forever blocking the low-hanging sun from ever reaching their deepest floors. It creates a permanent state of deep freeze, a cold so intense and consistent it's almost impossible to replicate here on Earth. Think of it as nature's most perfect and powerful deep freezer, operating silently for billions of years without ever being unplugged. This isn't just a theoretical concept. We have a real-world example right on our doorstep. Shackleton crater, located almost perfectly at the Moon's south pole, is one of the most famous of these shadow zones. It's a massive basin about 21 kilometers across and over 4 kilometers deep. Because of its precise location and depth, scientists are confident that some parts of its interior have been shrouded in absolute darkness for possibly 3 billion years or more. The temperature there is not just cold, it's profoundly cold, hovering around -240 degrees Celsius. At that point, molecular motion slows to a near standstill, and the very concept of decay as we know it practically ceases to exist. Our understanding of these eerie places comes from incredible feats of modern exploration. Orbital missions, particularly NASA's Lunar Reconnaissance Orbiter, which launched in 2009, have been absolutely pivotal. This spacecraft was equipped with incredibly sensitive instruments, like the Divina Lunar Radiometer experiment, which did something remarkable. It literally mapped the temperature of the entire lunar surface. By carefully measuring the heat radiated from the Moon, Divina created detailed thermal maps that definitively confirmed the existence of these permanently shadowed regions and precisely measured their frigid temperatures. This data didn't just prove they were cold, it revealed they were the coldest naturally occurring places we've yet found in our entire solar system, even colder than the surface of distant Pluto. This extreme and stable cold offers two monumental advantages for preserving delicate technology. First, it acts as an incredible preservative. Any material, whether it's an ancient ice sample or a sophisticated computer server, experiences degradation primarily through chemical reactions and physical stress. Heat accelerates these processes. In the deep cold of a lunar shadow zone, those damaging reactions are effectively paused, putting hardware into a state of suspended animation that could extend its functional lifespan for centuries, maybe even millennia. Second, for electronic equipment, heat creates what's known as thermal noise random interference that can corrupt delicate data signals. By eliminating this heat, the lunar environment also eliminates this primary source of noise, creating a perfectly quiet backdrop for storing and reading digital information with flawless accuracy. It's a natural solution to two of our biggest storage problems, just waiting for us in the darkness. While the moon's shadow zones present a fascinating solution, their necessity is driven by a problem unfolding right here at home, a challenge of staggering scale and urgency. We are in the midst of an explosive data generation event, a digital Big Bang that shows no signs of slowing down. To put the numbers in perspective, the global datasphere is projected to swell to a mind-boggling 175 zettabytes by 2025. Just one zettabyte is a 1 followed by 21 zeros. It's a volume of data so immense that if you tried to store it on standard 1 terabyte hard drives and stack them on top of each other, you would create a tower that could reach the moon and back over 20 times. This isn't just growth, it's an exponential surge, and our current infrastructure is buckling under the strain. The physical footprint of this data is becoming a critical issue. Massive data centers, some covering areas larger than multiple football fields, are proliferating across the globe, consuming vast tracts of land. But the real crisis lies in their insatiable appetite for energy. These facilities are voracious consumers of electricity, not just to power the servers themselves, but overwhelmingly to keep them from overheating. In fact, for a typical data center, cooling and power management can account for nearly 40% of its total energy consumption. This translates into a massive carbon footprint. Some estimates suggest the IT industry could be responsible for up to 20% of global electricity demand by the end of the decade, a level of consumption that is simply unsustainable in the long term. This creates a difficult paradox. Our pursuit of digital preservation is actively contributing to the environmental challenges we face. The very act of saving our history and knowledge is, in a tangible way, endangering our future. Beyond the environmental cost, there's the ever-present threat of physical vulnerability. Our most precious data repositories are concentrated in specific geographic locations, often near economic hubs or population centers, making them sitting ducks for a wide array of disasters. A single powerful hurricane, a devastating earthquake, or widespread flooding could wipe out irreplaceable archives in an instant. These aren't theoretical risks. We've seen time and again how natural disasters can cripple infrastructure and cause catastrophic data loss. And the threats aren't only natural, they are very human. In our interconnected world, data centers are prime targets for cyber attacks, from sophisticated ransomware campaigns that can hold entire cities hostage to state-sponsored espionage aimed at stealing or destroying critical information. Furthermore, these centralized repositories are vulnerable to geopolitical instability and conflict. A regional dispute or act of sabotage could sever access to or permanently destroy data that belongs to all of humanity, like global climate records or astronomical observations. Our current model puts all of our digital eggs in one very fragile and very terrestrial basket. As this deluge of data continues to grow, the limitations of our Earth-bound solutions are becoming impossible to ignore. We are hitting a wall in terms of space, energy efficiency, and most importantly, security. We cannot simply keep building bigger data centers with more powerful air conditioners. It's a losing battle on a finite planet. This escalating crisis is forcing scientists, engineers, and visionaries to look beyond our atmosphere for answers, to fundamentally reimagine where and how we preserve the digital cornerstone of our civilization. The need for a revolutionary approach isn't just about innovation for its own sake. It's about ensuring that the story of our time isn't lost to the very progress that created it. So why choose the moon for such a monumental task? It's not the only option beyond Earth, after all. We could place data centers in orbit closer to home. But the moon presents a unique and compelling set of advantages that neither our planet nor the orbital space around it can match. Its combination of proximity, permanence, and pristine environment makes it an ideal candidate for the most ambitious archival project in human history. Consider the alternative of orbital data storage. Imagine a fleet of massive server satellites circling the Earth. While they would be closer for data transmission, they would face a constant, invisible barrage of threats. The space around our planet is becoming increasingly congested with debris, from defunct satellites to tiny fragments of metal moving at 17,000 miles per hour. A single collision with even a small piece of this debris could be catastrophic, instantly obliterating a satellite and all the data it held. Furthermore, objects in low Earth orbit experience a slow but constant drag from the very outermost traces of our atmosphere, a force that gradually pulls them down, requiring regular boosts to maintain their position. This orbital decay is a relentless enemy of permanence. The moon, by beautiful contrast, is the most stable platform we could ask for. It is tidally locked to Earth, meaning the same side always faces us, providing a predictable and fixed point for communication. Its surface is utterly solid and unchanging, free from the gravitational tugs and orbital traffic jams that complicate life in Earth's orbit. Once a data vault is built and shielded on the lunar surface, it is there to stay. It won't drift, it won't require constant course corrections, and it is far less likely to suffer a catastrophic impact because the lunar environment, while not entirely empty, is exponentially less cluttered than the shell of space immediately surrounding our world. Then there's the matter of the environment itself. Here on Earth, our greatest enemies are the very elements that make life possible. Oxygen in our air causes oxidation and rust, slowly eating away at metal components. Humidity threatens delicate circuitry with condensation and corrosion. Dust particles can infiltrate and damage precision machinery. Our entire data storage industry is a constant, energy-intensive battle against these natural forces. The lunar environment, however, is a perfect vacuum. There is no air, no water, no weather, and no dust in the way we experience it. The regolith or lunar soil is a concern for moving parts, but a sealed vault would be immune to it. This absence of corrosive elements means hardware could potentially remain pristine for millennia, freed from the slow decay that plagues every machine on Earth. This combination of factors: proximity for manageable communication delays, a stable and permanent platform, and a benignly hostile environment that perfectly preserves technology, creates a proposition that is difficult to ignore. The moon offers a sanctuary. It provides a place where data can be left alone, secure in the knowledge that the forces which threaten it on Earth simply do not exist there. It's not just a cold, dark rock. It's a silent guardian, a natural fortress perfectly designed by circumstance to protect the most valuable things we own. This profound cold does more than just create a still environment. It fundamentally alters the very nature of matter and energy around it. To understand its power as a preservative, we need to think about heat not as a thing but as motion. At an atomic level, temperature is a measurement of vibration, the frantic dance of molecules. The warmer something is, the more violently its molecules shake and collide, and this constant, chaotic motion is the primary engine of decay. It breaks chemical bonds, causes materials to expand and contract, and gradually tears everything apart. Now, imagine slowly dialing down that motion. In the shadow zones, that dial is turned so far down that this molecular dance grinds to a near standstill. It's the difference between a raging mosh pit and a room where everyone is holding perfectly, silently still. In that stillness, the processes of degradation simply cannot gain any momentum. Time, for all practical purposes, is paused. This has a direct and massive impact on the hardware we would use to store data. One of the biggest enemies of a Chinese letter manufactured component is thermal expansion. Different materials expand and contract at different rates when heated or cooled. A standard hard drive, for instance, is a complex assembly of metal, plastic, and glass. On Earth, as it goes through daily and seasonal temperature cycles, these materials are constantly straining against each other, creating microscopic stresses and fatigue that eventually lead to failure. But in the constant, ultra-cold environment of a lunar crater, thermal expansion is virtually eliminated. The hardware would be held in a state of permanent, perfect dimensional stability. There's no expansion, no contraction, no mechanical stress. A solid-state drive placed there could theoretically remain physically intact for tens of thousands of years, free from the wear and tear that would destroy it in a terrestrial data center. The benefits extend deep into the chemistry of the devices as well. Here on Earth, corrosion is a relentless force. The oxygen in our air slowly oxidizes metal contacts, leading to increased electrical resistance and eventual failure. Humidity can lead to short circuits and the growth of destructive dendrites on circuit boards. Even without moisture, chemical interactions over time can degrade the performance of semiconductors. The lunar vacuum, combined with the extreme cold, slams the door on all of these chemical reactions. Without an atmosphere, there is no oxygen to cause oxidation. The cold itself acts as a powerful inhibitor, robbing chemical reactions of the energy they need to proceed. A microchip on the moon would be encased in a perfect, sterile, and frozen environment, protected from the chemical decay that is an inescapable fact of life on Earth. For the data itself, stored as delicate electrical charges or magnetic orientations, the cold provides another crucial advantage: electronic stability. In modern solid-state storage, like the flash memory in your phone or computer, data is stored in memory cells as tiny electrical charges. A fundamental problem is electron leakage, where these charges slowly drift away over time, especially as temperature increases, eventually leading to data corruption and bit errors. Heat essentially blurs the crisp, digital lines between a 1 and a 0. The extreme cold of the shadow zones acts like a perfect insulator, dramatically reducing this electron leakage. It keeps those electrical charges locked firmly in place, preserving the integrity of the data for far longer than would ever be possible in a warmer environment. This means the ones stay clearly defined as ones, and the zeros remain zeros for centuries, possibly even millennia. Ultimately, The most revolutionary aspect of this natural deep freeze is what it eliminates: the need for massive, complex, and energy-hungry cooling systems. On Earth, keeping a data center cool is a monumental and expensive engineering challenge, consuming enough electricity to power entire cities. On the Moon, that immense cooling requirement is provided for free by the environment itself. We wouldn't be fighting against nature to keep our servers cold. We would be leveraging nature's own perfect conditions. This isn't just an incremental improvement in efficiency, it's a complete paradigm shift. By harnessing this ancient, profound cold, we could create data vaults that are not only vastly more durable and secure, but also profoundly simpler and more sustainable in their operation. This lack of atmospheric protection presents a seemingly insurmountable obstacle, a constant rain of high-energy particles that would swiftly cripple any unprotected electronics. But the very characteristic that creates this vulnerability also holds the key to its solution. The lunar surface is blanketed in a layer of fine, rocky material called regolith, the product of billions of years of meteoroid impacts pulverizing the Moon's crust. This seemingly barren soil, this cosmic dust, transforms from a challenge for rovers into our greatest asset for protection. Instead of fighting the Moon's harsh reality, we can use its own geology to build a fortress. The concept is beautifully straightforward. We bury the vaults by excavating down just a few meters and covering the data storage modules with a thick layer of this readily available regolith. We create a powerful, passive radiation shield. It's a principle that has been understood for a very long time. Mass blocks radiation. On Earth, our atmosphere provides that mass in the form of a column of air. On the Moon, we simply replace that column with a blanket of soil. Studies from agencies like NASA suggest that a shielding layer of roughly 2 to 3 meters is sufficient to reduce radiation levels to a point that is not only safe for delicate electronics, but could even be safe for humans for extended periods. This isn't a hypothetical guess. It's engineering based on well-understood physics and data gathered from lunar missions. This approach of using in situ resources, or what's already available on site, is a game-changer in terms of efficiency and cost. The alternative, building above-ground facilities with walls made from imported, radiation-resistant materials like lead or specialized composites, would be astronomically expensive and logistically monstrous. Imagine the launch weight of enough material to shield an entire data center. By using the regolith, we eliminate that impossible burden. The shielding material is already there, waiting to be moved. Robotic excavators, perhaps solar-powered or even using local resources for fuel, could perform this task, piling this natural armor over the vault structures we deploy. This creates an incredibly resilient system. A regolith shield isn't just a static barrier, it's a self-healing one in a way. While a micrometeorite impact might chip away at a man-made material, a hit on a regolith berm would simply create a crater that could be easily filled back in by a maintenance robot using the very debris from the impact. The protection is maintained with minimal effort. This passive, resourceful method results in data vaults that are not just shielded, but are inherently robust and immune to the single biggest threat to electronics in space: the silent, invisible barrage of radiation that flows through the cosmos. We turn the Moon's greatest weakness into its most formidable defensive strength. This elegant solution presents a fascinating geographical puzzle, one that nature has already solved at the lunar poles. While the deep craters are locked in permanent night, their very rims and the surrounding highlands are often bathed in near-perpetual sunlight. This isn't a contradiction, it's a feature of the Moon's unique topography. Certain mountain peaks and crater rims, particularly at the poles, are known as peaks of eternal light. These are elevated points that, due to the moon's minimal axial tilt, are angled in such a way that the sun never dips below their horizon. They experience continuous daylight for months on end, with some areas illuminated over 80% of the time. It's the perfect power plant location, sitting literally in the backyard of the perfect deep freeze storage facility. Harnessing this power is remarkably straightforward and sustainable. We would deploy extensive arrays of solar panels across these brilliantly lit highlands. The efficiency of these panels would be far greater than anything possible on Earth. Our planet's atmosphere filters and scatters sunlight, significantly reducing its intensity by the time it reaches the ground. On the airless moon, there is no such interference. Solar panels there receive unfiltered, full-spectrum sunlight, making them vastly more productive per square meter. This means a smaller, simpler array can generate a tremendous amount of power, enough to run the computing hardware in the vaults below and keep the necessary support systems online. The next step is getting that power from the sunny peaks down into the dark craters. The most direct method would be to run physical power cables along the surface. While this might seem rudimentary, it's an incredibly robust and efficient technology. These cables would be designed to withstand the extreme temperature swings between the sunlit areas and the shadow, as well as the abrasive lunar dust. The distance involved would be relatively short, perhaps only a few kilometers from a sunlit ridge to a crater floor, making power loss over the transmission lines negligible. For even greater flexibility, we could employ wireless power transfer systems, using focused microwaves or lasers to beam energy down to receiving stations near the vaults. This technology is already in development on Earth and would allow for power delivery to multiple vault sites from a single, centralized solar farm. This setup elegantly sidesteps the need for complex and heavy alternative power sources. Nuclear generators, like the radioisotope thermoelectric generators used on deep space probes, provide reliable power but introduce significant complexity, cost, and regulatory hurdles. Large, chemical-based battery systems to store energy for the long lunar night would be massive, heavy, and prone to degradation over time. By strategically placing our solar arrays on these peaks of eternal light, we largely avoid the 2-week-long lunar night that blankets the rest of the moon. We can generate power almost continuously, requiring only a modest battery backup for the brief periods when a specific peak might rotate into shadow, ensuring an utterly reliable and uninterrupted energy supply. This creates a powerful and beautiful synergy. We are not fighting the lunar environment, we are partnering with it, using its most extreme and opposing characteristics in perfect harmony. The same craters that provide a natural, energy-free cryogenic preservation chamber are neighbored by highlands that provide a natural, relentless power source. It's a closed-loop system of incredible elegance, turning what might initially seem like a desolate and hostile landscape into the ideal location for a project of eternal significance. The moon itself provides both the vault and the power to maintain it. This physical separation creates a security advantage that is almost impossible to replicate on Earth. Think of it as the ultimate air gap. In cybersecurity, an air gap is a physical separation between a secure network and any other network, and it's considered the gold standard of protection because it makes remote hacking virtually impossible. A lunar data vault takes this concept to its absolute extreme. The gap isn't just a few feet of empty space, it's nearly 240,000 miles of vacuum. To even attempt a breach, a malicious actor wouldn't just need to find a software vulnerability. They would need to orchestrate a full-scale space mission, an endeavor requiring billions of dollars, a rare level of technical expertise, and the ability to launch rockets without being detected by the world's space agencies. The sheer cost and complexity of mounting a physical attack on a lunar facility makes it an almost unthinkable proposition, effectively deterring all but the most powerful and determined state-level threats. This isolation also allows us to design these archives with a fundamentally different philosophy towards connectivity. A data center on Earth is a living, breathing part of the internet, constantly sending and receiving information. This constant connection, while necessary for daily use, is its biggest weakness, providing countless entry points for cyber attacks. A lunar vault, however, doesn't need to be online. Its primary purpose is preservation, not daily access. We could design it to operate in a state of near total dormancy, only awakening for scheduled, infrequent data uploads or retrievals. The communication link to Earth could be designed as a one-way street for most of its life, receiving new data packages but never allowing external access to its internal systems. For even greater security, the most critical vaults could be designed with no receiving equipment at all, making them completely deaf to any incoming signals from Earth. They would be silent sentinels, holding their treasure until the day we decide to physically visit and retrieve it. This makes the Moon an ideal refuge for information that must survive any conceivable catastrophe on Earth. Governments could store backup copies of their most essential legal documents, national archives, and infrastructure blueprints, ensuring that even in the aftermath of a global conflict or a devastating asteroid impact, the foundational knowledge of a society could be recovered. Scientific organizations could preserve irreplaceable datasets from particle accelerators, genome sequencing projects, or decades of climate observation, safeguarding this hard-won knowledge against loss. This isn't just about backing up data, it's about insulating our collective memory from the very real risks of human error, conflict, and short-sightedness. It creates a permanent, off-site backup for civilization itself. Beyond catastrophic events, this isolation also provides a powerful defense against more mundane but equally damaging threats like corporate espionage, political manipulation, and the slow erosion of digital history. Cultural heritage stored on Earth is often subject to the changing winds of political ideology. Digital archives can be altered, censored, or deleted to suit a regime's narrative. But a copy of that same archive placed on the Moon exists outside any single nation's jurisdiction or control. It becomes a neutral, immutable record, a touchstone of truth that future generations can reference. In this way, the Lunar Vault transcends its role as a mere storage facility. It becomes a guarantor of authenticity, a place where information can be sealed away in a pristine state, free from the tampering and revisionism that so often plagues our history books. The Moon's quiet desolation, once a symbol of emptiness, becomes its greatest virtue, offering a sanctuary of permanence in a world of constant change. Of course, every grand vision must eventually confront the gritty details of reality, and the path to building these celestial libraries is paved with some of the most daunting engineering puzzles we've ever faced. The first and perhaps most formidable hurdle is the sheer act of getting there. Transporting the necessary materials from Earth to the Moon remains an extraordinarily expensive and complex endeavor. Every kilogram launched into space carries a tremendous cost, which means we can't simply ship prefabricated buildings or heavy machinery. Instead, we would need to be incredibly clever, designing modules that are as lightweight and compact as possible, perhaps even sent in pieces to be assembled on site like the most ambitious interstellar flat-pack furniture imaginable. This would necessitate a new era of supply chain logistics, with a steady stream of rocket launches delivering payloads with pinpoint accuracy to the lunar surface, all while minimizing the overall mass we need to lift out of Earth's gravity well. Once those first critical deliveries arrive, the real work begins. construction in an environment utterly alien to anything we've built in before. The moon's gravity is only 1/6 of Earth's, which might sound like it makes lifting heavy objects easier, but it introduces a host of other complications. Without the familiar weight and friction we rely on, standard construction techniques become almost useless. A simple turn of a wrench could send an astronaut or a robot spinning uncontrollably. The fine, abrasive lunar dust, or regolith, gets into everything, threatening to jam moving parts and damage sensitive electronics. This means the entire assembly process would almost certainly need to be performed by highly advanced autonomous robotic systems. We're not talking about simple remote-controlled machines. These would need to be intelligent robots capable of perceiving their environment, making complex decisions, and executing precise tasks with minimal human guidance, all while navigating the treacherous, shadowy terrain of the crater floors. The hardware they are tasked with assembling and maintaining must itself be a marvel of endurance engineering. These servers and storage drives won't be the off-the-shelf components we use today. They will need to be radically redesigned from the ground up to survive conditions that would instantly destroy any earthly device. Engineers will have to select materials that won't become brittle and shatter in the extreme cold or warp, and melt if briefly exposed to direct sunlight during setup. Every seal must be perfect to protect the delicate internals from the absolute vacuum of space, and they must be built to withstand a constant, low-level rain of micrometeorites, tiny particles of space dust traveling at incredible speeds that can pit surfaces and, over centuries, slowly erode away unprotected equipment. The design philosophy shifts from building for a 5-year lifespan to building for 5 centuries of flawless, unattended operation. This goal of long-term autonomy is further complicated by the unavoidable delay in communications. The moon is on average 240,000 miles away. Even traveling at the speed of light, a signal takes about 1.3 seconds to make a one-way trip. That means any command sent from Earth would take over 2.5 seconds to get a response. This might not sound like much, but it makes direct, real-time remote control of robots impossible for any complex or delicate task. Imagine trying to drive a rover using a live video feed that freezes for several seconds at a time. You'd crash into a boulder long before you realized it was there. This latency forces a complete rethinking of how we interact with lunar assets. Mission control on Earth would move from being a direct pilot to a high-level supervisor, sending up batches of instructions and objectives for the on-site robotic systems to interpret and execute independently using their own advanced sensors and artificial intelligence. This combination of factors, the brutal environment, the reliance on autonomy, and the communication lag, means that reliability isn't just a desirable feature, it is the single most important design criterion. Every system, from the smallest microchip to the largest solar panel, would need to be built with immense redundancy. If a component fails, there must be 2 or 3 backups ready to take over instantly. The robots themselves would need to be equipped with sophisticated diagnostic tools and repair capabilities, able to identify a failing power converter or a clogged filter and replace it using a stock of spare parts stored on site. The entire operation would be a symphony of predictive maintenance and fault tolerance, designed to hum along for decades without anyone there to hear it. Overcoming these challenges is less about a single breakthrough and more about a sustained commitment to systems engineering at its most robust and resilient, pushing the boundaries of what autonomous machines can achieve in the service of preserving human knowledge. Before a single byte of data can be stored in the lunar darkness, the stage must be set by a fleet of robotic pioneers. This initial phase isn't about grand construction. It's about meticulous preparation and proving that the entire concept is feasible. The workhorse of this endeavor will be a new class of autonomous rovers and landers, specifically designed for the unique challenges of the polar regions. These won't be the science-focused rovers we've sent to Mars. These will be the first construction workers on another world, equipped not with spectrometers and cameras, but with drills, scoops, graders, and robotic arms. Their primary mission is one of extreme terraforming on a miniature scale, to transform the chaotic, dusty, and treacherous terrain of a crater floor into a stable, level, and prepared building site. The Artemis program, with its goal of establishing a sustainable human presence at the lunar South Pole, provides the perfect catalyst and transportation network for these initial robotic scouts. Imagine an Artemis lander touching down not just with a crew module, but with a payload bay containing a dozen different specialized robots. They would be deployed one by one, each waking up to begin its specific task. The first out might be a reconnaissance rover, equipped with high-resolution LiDAR and ground-penetrating radar. Its job is to create a hyper-detailed three-dimensional map of the proposed vault site, identifying any hidden crevices, unstable slopes, or large boulders that could jeopardize construction. It's essentially conducting a geological survey to find the perfect, most stable patch of real estate in the perpetual night. Following close behind would be the excavators. These robots would be tasked with the first act of physical preparation, digging. Using robust, simple bucket drums or scoops, they would begin the process of leveling the chosen ground, creating a flat and stable foundation. But they wouldn't just be pushing dirt around, they'd be mining for our most valuable local resource, Regolith. Every scoopful of this excavated soil would be carefully collected and stockpiled. This isn't waste material, this is the future radiation shielding for the entire facility. The act of preparing the site and gathering the primary building material becomes one and the same, a perfect example of using in situ resources to dramatically reduce the need to launch heavy materials from Earth. Concurrently, other specialized landers would arrive, their cargo focused on establishing the vital lifelines of power and communication. One mission might deploy a small, modular solar array on a nearby sunlit peak, along with a simple power management unit. Another could land a robust communication beacon, a simple relay station that establishes the first dedicated data link between the shadowed crater floor and the lunar orbiting gateway station or directly to Earth. These initial systems would be small, designed for minimal power draw and maximum reliability, their sole purpose being to keep the early robotic workforce online and in contact. They are the humble beginnings of the vast network that will one day support the vaults themselves. The culmination of these early robotic missions would be the deployment of a Pathfinder, a small-scale, fully functional prototype of a data vault. This wouldn't be an exabyte-scale facility. It might be no larger than a shoebox containing a single solid-state drive or an experimental storage medium like quartz or Decay. The goal of this prototype isn't capacity, it's validation. Engineers on Earth would monitor it relentlessly, gathering data on its temperature stability, its power consumption, the integrity of its seals against the vacuum, and the performance of its data read/write functions over time. Did the Regolith shielding perform as expected? Did the electronics survive the initial thermal shock of the environment? This proof of concept phase is absolutely critical, working out the inevitable kinks and proving the technology on a small, low-risk scale before committing to the immense investment of a full-scale installation. The success of these first silent, robotic construction crews doesn't just pave the way, it literally prepares the ground for humanity's first permanent foothold of information beyond our world. But sending data to the moon isn't as simple as beaming a signal into the sky and hoping it arrives intact. The most immediate and tangible challenge is the sheer distance itself, which creates a fundamental and unavoidable delay. Because radio waves and laser light can only travel at the speed of light, a signal takes roughly 1.3 seconds to make the one-way trip from Earth to the moon. That means any communication has a minimum round-trip latency of about 2.6 seconds. This might not sound like much for sending an email, but for the massive, continuous data streams required to fill an off-world archive, this delay becomes a significant factor in designing the entire communication protocol. It means you cannot have real-time, interactive control of the systems on the lunar end. Instead, you must send large, carefully verified packets of data and then wait for a confirmation signal to come all the way back before proceeding, turning a simple data transfer into a carefully choreographed slow-motion dance. To handle the immense volume of data we'd need to send, we require a fire hose, not a garden hose. This is where traditional radio waves start to show their limitations. While perfectly reliable, radio frequency communication has a relatively narrow bandwidth, meaning it can only carry so much information at once. Sending exabytes of data over radio links would be agonizingly slow, like trying to fill an Olympic-sized swimming pool with a drinking straw. The solution, already being proven in space today, is optical communication, or lasercom. Instead of using radio waves, laser communication systems use focused beams of invisible infrared light to encode data. The key advantage is that light waves have a much higher frequency than radio waves, which allows them to carry orders of magnitude more information in the same amount of time. It's the difference between a single-lane country road and a multi-lane superhighway for data. NASA Laser Communications Relay Demonstration, or LCRD, has been a trailblazer in this field, operating from geostationary orbit since 2021. It has successfully demonstrated the ability to transmit and receive terabytes of data per day at speeds 10 to 100 times faster than traditional radio systems, all with significantly smaller, lighter, and more power-efficient equipment on the spacecraft. For a lunar data vault, this technology is transformative. A laser terminal on a lunar satellite or a ground station on Earth could establish a high-speed link with a receiver stationed on a sunlit peak near the vault. This optical link would allow us to upload enormous datasets, everything from the entire Library of Congress to a complete genomic database, in a matter of days or weeks instead of centuries. However, a laser's precision is both its greatest strength and its primary weakness. Because the beam is so incredibly narrow and focused, it requires extremely precise pointing between the transmitter and the receiver. Any slight misalignment, whether from vibrations on the lunar surface or atmospheric turbulence on Earth, can interrupt the connection. Furthermore, the beam can be scattered or completely blocked by something as simple as a thick cloud passing over the ground station on Earth. This is where redundancy and smart engineering come into play. To ensure an uninterrupted flow of data, we wouldn't rely on a single method or a single location. A robust lunar network would likely be a hybrid system. It would utilize multiple laser communication terminals spread across different locations on the moon and in orbit, paired with a fleet of dedicated relay satellites that could hand off the signal like a cosmic baton race. On Earth, we would build ground stations in multiple countries with different weather patterns, so if one station is cloudy, another can pick up the transmission seamlessly. Even with a perfect connection, the data itself needs armor. To guarantee that every single 1 and 0 arrives exactly as it was sent, despite the vast distance and potential for interference, we employ sophisticated error correction protocols. These are mathematical algorithms that add extra, redundant information to the data stream. This allows the receiving system on the Moon to not only detect if any bits were corrupted during the journey, but to actually reconstruct the original, perfect data without needing to ask for a retransmission and wait through another 2.6-second delay. It's like sending a puzzle with a few extra pieces. Even if some go missing, you can still see the complete picture. This end-to-end data integrity is non-negotiable for an archive meant to last millennia, ensuring that the digital time capsule we place on the Moon is a perfect, uncorrupted copy of the original. This communication infrastructure, born from the need to connect Earth with its lunar vaults, would do far more than just transfer files. It would lay the foundational groundwork for the next era of solar system exploration, creating the interplanetary internet that will one day connect missions throughout the inner planets. So what kind of information would be valuable enough to justify a journey to the Moon? It's a critical question, because not every cat video or social media feed deserves a spot in this celestial archive. The cost, while potentially coming down, will always be significant, so the data we choose to send must carry immense long-term value, representing the very essence of human knowledge and achievement that we simply cannot afford to lose. This isn't about everyday cloud storage. It's about curating a digital time capsule of civilization itself, designed to withstand any catastrophe Earth could possibly face. At the very top of this list would be our collective scientific heritage. Think about the irreplaceable datasets from monumental projects that can never be run again. The raw data from decades of climate and Earth observation satellites, a precise record of our changing planet that is absolutely vital for future generations to understand past environmental shifts. Or consider the petabytes of information generated by the Large Hadron Collider, the result of thousands of scientists working for years to uncover the fundamental secrets of the universe. These experiments are so vast and expensive that repeating them is unthinkable. Losing their data would be like burning a library of unique scientific discoveries. This also extends to astronomy. The deep field images from the James Webb Space Telescope or the gravitational wave readings from LIGO are snapshots of the cosmos that are both priceless and impossible to recreate. Preserving them off-world ensures that even if every observatory on Earth were destroyed, our window to the universe remains open. Equally crucial is the preservation of our biological blueprint. Genetic databases containing the sequenced genomes of millions of species, including humanity itself, would be a prime candidate for the ultimate backup. This goes far beyond human medical records. This is about safeguarding the fundamental code of life on Earth. If a global catastrophe were to cause a mass extinction event, these lunar archives could provide the instructions needed to help reintroduce or even reconstruct lost species, preserving planetary biodiversity. For humanity, it would serve as a biological Noah's Ark, ensuring that our genetic diversity isn't lost to a single planetary disaster. Alongside this, seed banks and vaults for cultural knowledge like agricultural techniques and medical research would form a complete recovery package, a guidebook for restarting civilization should the worst ever happen. Our cultural and historical identity must also have a place in this off-world library. This means creating digital copies of humanity's greatest achievements, the entire contents of the world's great libraries and museums, from the ancient texts of the Library of Alexandria to the works of Shakespeare and the music of Beethoven. It would include films, photographs, languages on the brink of extinction, and even the sprawling, chaotic creativity of the internet itself, captured in a massive snapshot. Projects like the Long Now Foundation's Rosetta Project, which aims to preserve all known human languages, are a perfect example of the kind of endeavor that would find a permanent home in a lunar vault. This ensures that the story of who we are, our art, our stories, our languages, and our shared history survives long after the original artifacts may have turned to dust, preserving the human spirit itself for millennia to come. On a more practical level, governments and global organizations would have a powerful incentive to store critical operational data. This includes backup copies of essential legal frameworks, national constitutions, international treaties, property records, and the core codes that underpin our digital infrastructure. In the aftermath of a global crisis, whether caused by nature or human conflict, the ability to recover these foundational documents would be paramount to re-establishing order, law, and society. For private entities, the vault could offer an unparalleled service for protecting intellectual property on a grand scale. The secret formulas for life-saving pharmaceuticals, the source code for critical software, the architectural plans for major innovations, all could be sealed away in a neutral, secure location, immune to corporate espionage, hostile takeovers, or the simple failure of a company over centuries. By being so selective, we ensure that the Lunar Vault isn't just a storage unit, but a strategic investment in the continuity and recovery of our entire species, protecting what matters most from any threat, known or unknown. The staggering price tag of reaching the moon is the single largest hurdle in any economic analysis, a formidable barrier that cannot be ignored. Currently, launching just 1 kilogram of payload to the lunar surface can cost well over $1 million using traditional methods. This means that sending even a modest, compact server rack could carry a launch cost comparable to that of a luxury private jet. This isn't just expensive, it's prohibitively so for all but the most well-funded entities. However, this daunting economic landscape is undergoing a radical transformation, driven primarily by the rise of private space companies championing reusability. When a rocket's first stage can land itself on a drone ship and be refueled and reflown, the economics of spaceflight shift from a custom-built, one-time extravaganza to something closer to a commercial airline model. This dramatic reduction in per-kilogram cost is the key that unlocks the entire concept, turning a lunar vault from a fantastical thought experiment into a project with a conceivable business plan. Further driving down expenses is the powerful potential of collaboration and shared missions. Just as companies today co-locate their servers in massive third-party data centers to share the burden of infrastructure costs, we could see a future where multiple nations, global corporations, or scientific consortia pool their resources to fund a single lunar vault mission. A single SpaceX Starship or a similar heavy-lift vehicle of the future could carry storage modules for a dozen different clients in one trip, drastically slashing the individual cost for each participant. This shared risk, shared reward model transforms the venture from a solitary, monumental expenditure into a collaborative investment, making it accessible to a wider range of organizations that have critical data to preserve but lack the budget for a solo lunar mission. Once the vault is operational, the long-term financial benefits begin to crystallize, slowly but surely offsetting that massive initial investment. The most immediate and dramatic saving comes from the complete elimination of energy costs for cooling. On Earth, the electricity required to run the powerful air conditioning and liquid cooling systems in a major data center is a perpetual multi-million-dollar annual expense. On the Moon, this cost is zero. The natural environment provides a perfect cryogenic state for free forever. This alone represents a saving so significant that, when projected over a century or more, it could pay back a substantial portion of the original launch and setup costs. Furthermore, the hardware within these vaults, shielded from oxidation, humidity, and thermal stress, would experience a lifespan measured in centuries rather than years. The relentless cycle of replacing failed hard drives and outdated servers every 3 to 5 years would come to an end, representing another massive saving on both equipment and the labor required to maintain it. Yet the most compelling economic argument might not be found on a traditional balance sheet. It lies in the realm of risk mitigation and the preservation of value that is truly irreplaceable. How do you calculate the financial value of ensuring that humanity's scientific, cultural, and genetic data survives a global catastrophe? For a government, the cost of launching a backup of its most essential national archives is minuscule compared to the incalculable cost of losing them forever in a war or a natural disaster. For a pharmaceutical company, the value of preserving the molecular formula for a blockbuster drug or a promising cancer treatment is worth far more than the price of securing it in a vault that is immune to espionage, fire, or flooding. This isn't just about saving money, it's about ensuring our collective future against existential threats. The Lunar Vault becomes a premium insurance policy for civilization itself, a one-time premium that guarantees a payout of knowledge and recovery should the worst ever occur. As we look to the coming decades, the economic trajectory points firmly toward greater viability. Launch costs are expected to continue their downward trend as reusability becomes standard and competition in the launch industry intensifies. Simultaneously, the technology for data storage is advancing at a breathtaking pace, with new mediums like DNA storage or 5-dimensional quartz offering densities that would allow us to store exabytes of data in a container the size of a sugar cube. Sending a gram of this ultra-dense storage to the moon would be vastly more cost-effective than sending a kilogram of today's hard drives. This convergence of cheaper transportation and vastly more efficient storage media will inevitably push lunar data storage from the realm of government projects and ultra-wealthy visionaries into a competitive commercial market, offering a unique and invaluable service for preserving what we simply cannot afford to lose. This shift in perspective forces us to ask a critical question. Could moving our data off-world actually be a greener choice for the planet? The environmental toll of our digital lives is staggering and often hidden from view. Here on Earth, massive data centers guzzle incredible amounts of electricity, not just to power the servers but overwhelmingly to keep them from overheating. In fact, cooling can account for nearly 40% of a facility's total energy draw. That translates to a huge carbon footprint, with the global IT sector's energy appetite rivaling that of entire countries. Furthermore, these centers consume billions of gallons of precious fresh water annually for cooling towers, a resource that is becoming increasingly scarce in many parts of the world. The very act of preserving our digital world is ironically contributing to the degradation of our physical one. This is where the lunar model presents a fundamentally different paradigm. By harnessing the moon's natural deep freeze environment, we completely eliminate the single largest energy drain of traditional data storage, active cooling. The shadow zones provide a perfect, stable cryogenic state absolutely free of charge, 24 hours a day, 365 days a year with zero electricity required. This isn't just an incremental improvement in efficiency. It's a complete elimination of an entire category of energy consumption. The power needed would be dedicated solely to running the servers themselves and maintaining basic systems, a fraction of the load required for an equivalent facility on Earth. The energy that is required can be sourced with remarkable cleanliness and efficiency. As we've discussed, the adjacent peaks of eternal light at the lunar poles offer a virtually uninterrupted supply of solar energy. Without an atmosphere to filter or scatter sunlight, lunar solar panels operate at peak efficiency, generating far more power per square meter than their terrestrial counterparts ever could. This creates a closed-loop system where the power for the vaults is generated right next door on the moon itself, using a renewable resource. There are no fossil fuels burned, no carbon emissions produced at the point of use, and no strain on Earth's energy grids. From an operational standpoint, a lunar data vault could achieve a level of sustainability that is simply unattainable anywhere on our planet. Another profound environmental advantage lies in the lack of a local ecosystem to disrupt. Constructing a new data center on Earth often means clearing land, diverting water sources, and impacting local wildlife. On the moon, there is no life, no water table to contaminate, and no atmosphere to pollute. The construction process, while complex, would have no direct ecological footprint on its immediate environment. We are building in a place that is, from a biological perspective, already a sterile void. This allows us to pursue large-scale infrastructure projects without the ethical dilemma of environmental damage or habitat loss. However, to get a complete picture, we must also confront the significant environmental costs associated with actually getting to the moon. Rocket launches are not clean endeavors. A single launch can emit substantial amounts of carbon dioxide and other particulates into the upper atmosphere, and the manufacturing processes for rockets and their fuel are energy-intensive. This is the largest counterargument to the green narrative of lunar vaults. The key to mitigating this impact lies in the same principles of sustainability we apply on Earth: advancement and efficiency. The industry is already moving rapidly toward reusable rockets, which dramatically reduce the waste and energy required per kilogram of payload delivered to space. Companies are also investing in cleaner propulsion technologies, such as methane-fueled engines that could be more efficient and less polluting. Furthermore, the sheer longevity of the lunar infrastructure must be factored into this equation. While a rocket launch has a one-time environmental cost, the data vault it helps build is designed to operate for centuries with minimal further input. When you amortize the initial launch emissions over hundreds of years of flawless, energy-efficient operation, the per-year environmental impact becomes far more favorable. Compare that to an Earth-based data center, which requires a constant, never-ending input of energy and water for its entire operational life, and which itself had a construction footprint of concrete, steel, and land use. The lunar model trades a large upfront environmental cost for centuries of virtually impact-free operation, while the terrestrial model involves a lower initial cost but a perpetual, ongoing environmental penalty. The ultimate goal is to create a truly sustainable cycle, perhaps one day using resources mined from the moon or asteroids to build and fuel further expansion, minimizing the need to launch everything from Earth. While the path isn't perfectly green from the very first mission, the direction of travel points toward a future where humanity's expansion into the solar system can be done thoughtfully. Lunar data storage doesn't just offer a solution to a digital crisis. It challenges us to envision a new paradigm for infrastructure, one that works in harmony with the environment, even if that environment is the silent, empty space of another world. But this ambitious vision of a lunar archive immediately raises a profound and complex question that transcends engineering. Who exactly gets to make the rules once we get there? The legal framework for any activity on the moon is not a blank slate. It is currently governed by a foundational document from the era of the Apollo missions, known as the Outer Space Treaty of 1967. This treaty, which has been ratified by over 100 countries including all the major spacefaring nations, establishes some crucial principles. Most importantly, it explicitly states that outer space, including the moon and other celestial bodies, is not subject to national appropriation by any means. No country can plant a flag on the moon and claim it as its own sovereign territory. This principle was designed to prevent a colonial land rush in space and to ensure that these new frontiers are developed for the benefit of all humanity. However, this well-intentioned prohibition on claiming territory creates a significant gray area when it comes to the things we might place on that territory, such as a data vault. If a nation or a private company builds a facility on the lunar surface, who has jurisdiction over the data inside it, does the data fall under the laws of the country that owns the company? The country that launched the rocket, or does it exist in a new kind of legal limbo, a digital extraterritorial zone? This isn't just an academic debate, it has real-world implications. If a dispute arises over data access, ownership, or a potential security breach, which court has the authority to adjudicate? The current treaty provides a framework for peaceful use, but offers very little guidance on these specific, tangible issues of property and data rights that are essential for a functioning commercial or scientific enterprise. This legal ambiguity extends directly to the critical issues of data security and privacy. Imagine a scenario where a multinational consortium stores a global health database in a lunar vault. Who is permitted to access that sensitive information? What protocols would prevent a single member nation from exploiting it for its own gain? Or consider the personal data of private citizens stored for archival purposes. How do we guarantee their privacy rights are protected by a facility that is, technically, outside any nation's legal jurisdiction? Without clear international agreements establishing universal standards for data handling, encryption, and access control, these lunar vaults could become lawless digital frontiers, vulnerable to exploitation by the most powerful entities. The very isolation that makes them secure from physical threats could also make them secure from legal accountability. Beyond the purely legal questions, the development of lunar data storage forces us to confront deep ethical dilemmas. The most pressing of these is the potential to exacerbate the existing digital divide on a cosmic scale. The cost of securing a spot in a lunar vault will be immense, at least initially. This creates a real risk that only the wealthiest governments, the most powerful corporations, and the most developed nations will be able to afford to preserve their knowledge and their history. The stories, languages, and cultural records of smaller or less wealthy nations and indigenous communities could be left behind, effectively editing them out of humanity's off-world backup. This isn't just about losing data. It's about whose version of history gets to be remembered for the millennia to come and whose fades into oblivion. We must proactively work to ensure that this technology becomes a tool for universal preservation, not a new vector for inequality. This leads to the darker but necessary consideration of how such a secure and remote archive could be misused. In the wrong hands, a lunar data vault could become the ultimate tool for oppression, a place to lock away incriminating evidence, historical truths, or sensitive information with the intention of it never being found or accessed by anyone else. The same technology designed to protect our collective heritage could be perverted to bury the darkest secrets of a regime, ensuring they never come to light. The potential for creating a permanent, inaccessible black box of information is a serious threat that must be addressed through transparent governance before the first module even lands. Navigating this intricate web of legal and ethical challenges will require unprecedented levels of international cooperation and multi-stakeholder collaboration. It cannot be left solely to space lawyers and diplomats. It requires input from ethicists, historians, technologists, and representatives from civil society across the globe. We may need a new international body or a specific addition to the existing framework of space law, something akin to a lunar data accord. This agreement would need to establish clear rules of the road, defining data ownership, ensuring equitable access, mandating transparency in operations, and creating mechanisms for dispute resolution. The goal would not be to stifle innovation but to guide it responsibly, ensuring that humanity's first permanent foothold of information beyond Earth reflects our highest ideals of fairness, openness, and shared benefit rather than our deepest flaws. Let's bring this grand vision into sharper focus with a detailed look at Project Lunar Archive, a comprehensive theoretical model that stitches together all the concepts we've discussed into a single, cohesive blueprint. This isn't just a vague idea. It's a fully imagined system designed to demonstrate the practical feasibility of a lunar data vault, from the initial landing to centuries of flawless operation. Think of it as the architectural plans for humanity's first library on another world, a detailed prototype that allows engineers to stress-test every assumption and solve problems on paper long before a single rocket ever leaves the launch pad. The entire operation would be built around a philosophy of modularity and redundancy. Instead of constructing one massive, monolithic structure, the archive would consist of numerous self-contained units, each about the size of a standard shipping container. These modules would be launched separately, perhaps over the course of several missions, and then linked together on the lunar surface like building blocks. This approach offers incredible flexibility. If one module were to fail, it could be isolated and replaced without jeopardizing the entire archive. More modules could be added over time as storage needs grow, allowing the facility to expand organically. Each unit would be a hardened fortress in its own right, designed to be entirely self-sufficient with its own independent power regulation, internal communication bus, and basic computing for system diagnostics. Upon landing, the first and most critical phase would be what engineers call in situ resource utilization, put simply, using the moon's own dirt for protection. Autonomous robotic bulldozers and excavators deployed from the same lander would immediately get to work. Their task would be to dig a trench in the permanently shadowed regolith, carefully lower the data storage module into its grave, and then meticulously cover it with a 2-meter-thick blanket of the excavated soil. This isn't just a simple burial. The regolith would be carefully compacted and contoured to form a stable, protective berm that shields the module from radiation and the constant threat of micrometeorite impacts. This entire process would be automated, with the robots guided by sophisticated LiDAR and AI to ensure precision in the treacherous low-light environment. The choice of storage medium inside these modules is where Project Lunar Archive truly leaps into the future. It moves far beyond the magnetic platters and flash memory we use today, embracing technologies being pioneered in labs right now that are almost unimaginably durable and dense. One leading candidate is 5-dimensional optical data storage in quartz glass. This technique uses femtoscanned lasers to etch nanoscale structures into a small, stable glass disc. These structures alter the way light travels through the glass, encoding information in 5 distinct dimensions. The 3 physical dimensions of the nanostructure, plus its orientation and the light intensity it creates. A single DVD-sized disk of this material could theoretically store 360 terabytes of data, the equivalent of several entire national libraries, and withstand temperatures of over 1,000 degrees Celsius without damage. Another contender is digital DNA storage, which encodes ones and zeros into the 4 base sequences of synthetic DNA molecules. This medium boasts an almost absurd data density. All of the world's digital data could theoretically be stored in a container roughly the size of a few sugar cubes, and DNA itself has a proven half-life of over 500 years, even in imperfect conditions. On the Moon, in a constant deep freeze, that information could remain perfectly intact for hundreds of thousands of years. Keeping this entire system running for centuries requires a radical rethinking of maintenance. Human repair technicians won't be making house calls. Instead, the archive would be tended to by a small, permanent population of autonomous caretaker robots. These machines would reside in a small, shielded garage module, spending most of their time in a low-power hibernation state, on a regular schedule, or if summoned by an alert from the vault's internal diagnostics, they would awaken and venture out to perform their duties. Their tasks could range from the simple, like using a brush to clear wind-blown dust from a solar panel on a nearby peak, to the complex, such as using a robotic arm to physically disconnect a failing power regulator in a storage module and replace it with a spare part from an on-site depot. They would be equipped with advanced machine vision to navigate the difficult terrain and sophisticated manipulators to perform delicate repairs. Their prime directive would be autonomy. They must be able to identify a problem, locate the solution, and execute the fix with only high-level oversight from Earth, overcoming the crippling communication delay through their own onboard intelligence. This case study of Project Lunar Archive does more than just paint a compelling picture. It serves as a vital tool for identifying the real-world challenges and bottlenecks. It forces engineers to ask difficult questions. How do we test the long-term reliability of a DNA storage drive in a vacuum chamber that simulates lunar conditions for decades? What is the optimal communication protocol for a network that must operate with a 2.5-second lag? How many spare parts need to be prepositioned to ensure a 99.99% reliability over a 500-year period? By working through these questions in a detailed theoretical model, we move from speculative fantasy to actionable engineering. Project Lunar Archive provides the essential blueprint, the shared vision that allows scientists, corporations, and governments to align their research and development, turning the Moon's silent shadows into the final safeguard for our digital soul. This grand undertaking is far too vast and complex for any single entity to tackle alone. It demands a fusion of two very different worlds, the seasoned, methodical expertise of government space agencies and the agile, disruptive innovation of the private tech sector. Each brings a unique and essential piece of the puzzle to the table, and their collaboration is the only way to turn this science fiction vision into science fact. It's a partnership where the art of the possible meets the business of the practical. Space agencies like NASA and the European Space Agency are the veteran architects of off-world exploration. They possess the hard-won, irreplaceable knowledge of how to simply get to the Moon and operate there. Their decades of experience have given them a deep understanding of the brutal lunar environment, the radiation profiles, the thermal extremes, the properties of the regolith, and the unforgiving nature of orbital mechanics. They are the masters of mission assurance, of building systems that are not just efficient, but supremely reliable and safe. For a lunar data vault, they would provide the foundational bedrock, the launch vehicles, the landing systems, the proven designs for habitats and power systems that can survive the long lunar night, and the operational protocols for working in such a hostile place. They are the ones who know how to build the house and make sure it doesn't collapse. The private tech industry, on the other hand, brings the tools to fill that house with meaning and purpose. Companies like Google, IBM, Amazon Web Services, and a host of specialized storage startups are engaged in a relentless, high-stakes race to redefine the very limits of data. They are pushing the boundaries of storage density with technologies like helium-filled drives and advanced NAND flash. They are pioneering revolutionary new mediums like synthetic DNA and 5-dimensional quartz storage. and they are masters of the software that manages exabytes of information across global networks. Their entire business model is built on efficiency, scalability, and innovation at a pace that traditional aerospace simply cannot match. They would provide the beating heart of the vault, the actual storage hardware, the error correction algorithms, the encryption protocols to keep data secure, and the energy management systems to run it all on a tight power budget. The most effective model for harnessing these complementary strengths is the public-private partnership. This approach allows for the pooling of resources and, just as importantly, the sharing of risks. A space agency might fund the initial transportation and infrastructure development, while a consortium of tech companies invests in the data storage payloads and their maintenance. This spreads the enormous financial burden across multiple stakeholders, making the project more viable for everyone involved. Furthermore, it accelerates development dramatically. Instead of a space agency spending years and billions of dollars developing a new data storage technology from scratch, it can leverage the cutting-edge work already being done in Silicon Valley labs, adapting it for the lunar environment. Conversely, tech companies gain access to a revolutionary new market and a testing ground for their most advanced technologies, all while being guided by the agencies that know how to operate in space safely. We are already seeing the framework for this kind of international and commercial cooperation taking shape with initiatives like the Artemis Accords. This set of principles, signed by dozens of nations, establishes a practical framework for peaceful lunar exploration and sets out guidelines for things like interoperability of systems, emergency assistance, and the transparent sharing of scientific data. It creates a rules-based environment that gives private companies the confidence to invest, knowing there are agreed-upon standards and practices. We can easily imagine a future where a mission to deploy a data vault is a joint effort. A NASA lander carries a ESA-built communications module and a power system developed by a private aerospace firm, all delivering data storage hardware designed and funded by a partnership between Google and a DNA storage startup. This multi-stakeholder model is no longer a fantasy. It is the established direction of travel for the new space age, and it is the essential engine that will power humanity's next giant leap in preserving its knowledge. But to truly understand the revolutionary nature of these new storage mediums, we need to appreciate just how fragile and short-lived our current methods really are. The hard drives in our computers and the solid-state drives in our phones are marvels of modern engineering, but they are built for convenience and speed, not for eternity. A typical hard drive, with its spinning magnetic platters and delicate read-write heads, has a functional lifespan measured in just a handful of years before mechanical wear or magnetic decay begins to corrupt its data. Even the more robust solid-state drives, which have no moving parts, suffer from a phenomenon called electron leakage, where the tiny electrical charges that represent our ones and zeros slowly fade away over time, especially when exposed to heat. On Earth, in a temperature-controlled data center, we fight this inevitable decay with constant power, active cooling, and a relentless cycle of copying data to new drives every 3 to 5 years before the old ones fail. This entire energy-intensive, high-maintenance model is completely unsustainable for a vault on the moon designed to operate silently for millennia without a single human touch. We need to move beyond electronics altogether and embrace a new class of storage that is, in essence, a form of permanent inscription. This is where the concept of synthetic DNA data storage enters the picture, and it sounds like something ripped from the pages of the most ambitious science fiction. The principle, however, is grounded in beautiful biological logic. life on Earth has already perfected a system for storing and transmitting immense amounts of information across thousands of generations, the DNA molecule. This incredible molecule is astoundingly dense and durable. Just 1 gram of DNA is theoretically capable of storing 215 petabytes of data. That's 215 million gigabytes. To put that in perspective, all of the data in the entire world could potentially be stored in a container of DNA no larger than a few shoeboxes. The process works by translating the binary code of digital data, the strings of ones and zeros, into the 4-letter chemical code of DNA, A, T, C, and G. Sophisticated machines then synthesize actual strands of DNA with that specific sequence. To read the data back, you simply sequence the DNA, just like scientists do for the human genome, and then translate the chemical code back into binary. The longevity is the real miracle. We have successfully sequenced DNA from mammoths and Neanderthals that is tens of thousands of years old. On the Moon, sealed in a vial and kept in a perpetual deep freeze, synthetic DNA could preserve information for potentially millions of years, making it one of the most future-proof mediums imaginable. For those who find the biological approach a little too unconventional, there is a more mineral-based candidate that is equally extraordinary: 5-dimensional data storage in quartz glass. Developed initially at the University of Southampton, this technology uses a femtosecond laser, which fires incredibly short and intense pulses of light to inscribe tiny nanostructures into a small, pure disk of fused quartz glass. These nanostructures alter the way light travels through the glass when it's read back using a combination of an optical microscope and a polarizer. The information is encoded in 5 distinct dimensions of the light that passes through these structures, the 3 traditional spatial dimensions, plus 2 additional optical properties: the intensity and the orientation of the light wave. This 5th dimension is what gives the technology its name and its incredible capacity. A single disc roughly the size of a standard DVD can hold 360 terabytes of data, and it is phenomenally resilient. The quartz glass can withstand searing heat up to 1000 degrees Celsius. It is completely waterproof, and it is immune to the effects of magnetic fields and radiation. It is, for all intents and purposes, a permanent and indestructible stone tablet for the digital age, perfectly suited to the stable environment of a lunar vault. Of course, simply choosing a durable medium is only half the battle. We must also ensure the data itself is armored against the slow, creeping errors of deep time. This is where advanced error correction coding becomes absolutely critical. Even the most stable storage medium could theoretically experience subtle degradation over hundreds of thousands of years. To combat this, we wouldn't store the raw ones and zeros of our data. Instead, we would encode it with sophisticated mathematical algorithms that add a significant amount of redundant information. Think of it like sending a very important message where every word is repeated 3 times. Even if one copy gets smudged or lost, you can still perfectly reconstruct the original from the remaining 2. These error correction schemes, like Reed-Solomon codes or newer fountain codes, are so powerful that they can allow a future civilization to recover 100% of the original data, even if large portions of the physical storage medium have become corrupted or unreadable. We would essentially be building a self-healing archive where the information itself contains the instructions for its own repair and recovery, ensuring its integrity across eons. Finally, the overall strategy for the vault itself must embrace the oldest and most reliable principle of data backup: redundancy, redundancy, redundancy. We would never store a single, priceless copy of humanity's knowledge in one place. The Lunar Archive would be a distributed system, with multiple identical copies of the entire dataset stored in several different shadowed craters, spaced far apart across the lunar poles. This geographical distribution safeguards against any localized catastrophe, such as a rare but possible large meteorite impact directly on one vault site. If one facility were destroyed, the others would remain perfectly intact, preserving the complete record. This multi-site approach mirrors the best practices of terrestrial data centers, but on a planetary scale, creating a resilient and fault-tolerant network of knowledge that would be virtually impossible to erase completely. By combining these ultra-stable physical mediums with intelligent data encoding and strategic distribution, we aren't just storing data for a few decades. We are creating a time capsule designed to survive, intact and readable, for longer than human civilization has existed, a gift of memory from our present to an unimaginably distant future. Imagine a future where every language, every story, and every song we've ever created isn't just stored in a museum or on a server farm, but is placed in a sanctuary beyond the reach of any disaster. This is the profound shift in thinking that lunar data vaults represent. It's not merely a backup, it's a promise that the creative and intellectual output of our species, the very things that make us human, will have a witness in the universe long after our cities may have turned to dust. This transforms a technical project into a deeply humanistic endeavor, an act of faith in the future that connects us to every generation that came before us who sought to leave their mark on the world. Think about the vast tapestry of human expression that is currently at risk. We have digitized millions of books, paintings, and musical compositions, but these digital copies reside on media that degrades and in locations vulnerable to everything from flooding to cyber warfare. A lunar vault could contain the entire compiled works of humanity, every novel from Austen to Zora Neale Hurston, every symphony from Beethoven to modern film scores, every painting from the caves of Lascaux to the digital art of today. It would safeguard the foundational texts of civilizations, religious scriptures, philosophical treatises, and the original documents that shaped nations. This wouldn't be a curated collection for the elite. It would be the ultimate public library, a complete archive of our collective soul, designed for recovery and rediscovery by anyone who might need it centuries or millennia from now. Perhaps the most urgent cultural rescue mission involves language itself. We are in a race against time as languages disappear at an alarming rate, taking with them unique worldviews, oral histories, and cultural knowledge that can never be recovered. Projects like the Long Now Foundation's Rosetta Project are already creating physical, microscopic etchings of linguistic information, but a lunar vault could host a digital version of this on an unimaginable scale. It could store not just dictionaries and grammar guides, but high-quality recordings of native speakers, stories told in their original tongue, and explanations of cultural concepts that simply don't translate. This would ensure that even if a language falls silent on Earth, its complete record and sonic beauty are preserved forever elsewhere, a gift of identity to any descendants who might one day seek to reclaim it. This endeavor forces us to confront a vital question: who gets to decide what is saved? The selection process for such an archive would be one of the most significant cultural projects in human history. It would require a global, collaborative effort involving linguists, historians, artists, and community leaders from every corner of the world to ensure the archive is truly representative of humanity in all its diversity, and not just the dominant cultures of the day. The goal would be to avoid creating a monolithic, singular narrative of history, but instead to preserve a multitude of voices, perspectives, and truths, including the difficult and painful chapters of our past. This inclusive approach would make the Lunar Vault a neutral ground for history, protecting contested knowledge and alternative viewpoints from the erosion of time and the rewriting of history by those in power. Ultimately, the cultural significance of this project echoes the deepest human impulses we've always had, to make our mark and to speak to the future. From the ancient Egyptians building pyramids to Voyager's golden record sailing into interstellar space, we have always sought ways to say, "We were here." A lunar data vault is the modern, digital embodiment of that same timeless urge, but on a scale never before attempted. It is our pyramid, our library of Alexandria, our cave painting for the digital age. By taking this step, we are doing more than preserving data. We are affirming the value of our existence and making a solemn commitment that the light of human creativity, in all its forms, will never be extinguished. Even the most brilliantly engineered systems must contend with the unpredictable nature of the cosmos, and a lunar data vault is no exception. While the Moon offers a uniquely stable environment, it is not without its own set of hazards that could threaten the integrity of these precious digital repositories over centuries of unsupervised operation. The strategy for safeguarding this information isn't about creating a perfect, failure-proof system. That's an impossible goal, but about building a deeply resilient one, with layers of defenses designed to anticipate, withstand, and recover from any conceivable problem. This philosophy of resilience turns a fragile single point of failure into a robust, living network of information that can endure long after its creators are gone. The first and most fundamental layer of defense is the principle of redundancy, implemented at every conceivable level. Within a single vault module, this means no single point of failure for critical components. Power systems wouldn't rely on one solar array. They'd be fed by multiple independent units on different sunlit peaks, with robust power routing that can isolate a failed line. The storage hardware itself would be arranged in massive, distributed arrays, similar to the RAID systems used in terrestrial data centers but on a monumental scale. If one drive or even an entire server rack were to fail, the data would be seamlessly reconstructed from the information striped across dozens of other units. This internal redundancy ensures that small, localized failures are nothing more than temporary blips, automatically corrected without any loss of information. This concept expands dramatically beyond the walls of a single facility. The most crucial safeguard against a catastrophic event, like a direct meteorite strike, is geographical distribution. Instead of one grand lunar library, the complete archive would be replicated across multiple vault sites, strategically placed in different shadowed craters far apart from one another. This means that even if a rare, large impact event were to completely obliterate one entire vault complex, the other sites would remain untouched, preserving a complete and intact copy of the entire dataset. This distributed model mirrors the best practices of cloud storage on Earth but on a planetary scale, ensuring that the loss of any single location, no matter how devastating, is never a fatal blow to the entire project. The archive becomes a multi-headed hydra. Cutting off one head does not kill the creature. To maintain these systems over centuries requires a shift from scheduled maintenance to predictive and autonomous repair. This is where advanced robotics and artificial intelligence become the unsung guardians of the vault. A permanent crew of autonomous caretaker robots would be stationed at each site, living in a shielded garage module. These wouldn't be simple remote-controlled arms. They would be sophisticated machines equipped with advanced machine vision, sensitive diagnostic tools, and a deep learning understanding of the entire facility's schematics. Their primary role would be one of constant, quiet vigilance. They would perform regular patrols using thermal and acoustic sensors to listen for the telltale signs of a failing power converter or a pump nearing the end of its lifespan. Using predictive algorithms, they could identify components that are likely to fail in the coming months or years and proactively replace them during scheduled maintenance windows using a vast on-site depot of spare parts. This transforms maintenance from a reactive process waiting for something to break to a proactive one, preventing problems from ever occurring in the first place. The very design and selection of materials for every component must be rethought for longevity. On Earth, we design for a lifespan of 5 to 10 years. For the lunar vault, every seal, every wire, every microchip must be designed and tested for a minimum of 500 years of reliable operation. This means moving away from materials that degrade under constant radiation or become brittle in extreme cold. Plastics and polymers that might outgas or break down over centuries would be replaced by ceramics, specially formulated metals, and glass. Connectors and moving parts would be designed with immense tolerances to prevent seizing in the vacuum. Shielding would be integral, not an afterthought, with the Regolith berms acting as a first line of defense, and each component's housing providing an additional layer of protection. This obsessive focus on material science ensures the hardware itself becomes a time capsule, as durable as the data it contains. Finally, there must be an acknowledged last resort, the contingency plan for physical recovery. Despite every precaution, there remains a remote possibility of a cascading failure that renders a vault site incommunicado and unable to function. For this scenario, the archive must be designed for eventual physical retrieval. This means the storage media, whether they are quartz disks or vials of synthetic DNA, would be housed in standardized, ruggedized containers clearly marked and easily accessible by a future human or robotic recovery mission. These containers would be the final, physical manifestation of the data, designed to be picked up, loaded onto a lander, and returned to Earth for analysis. This final layer of the plan accepts that while we strive for perfect autonomy, we are also building a bridge for our descendants, ensuring that even if the vault falls silent, the knowledge within it is never truly lost, only waiting for a future generation to come and bring it home. The success of a lunar archive hinges not just on the brilliance of its engineering, but on capturing the imagination and securing the trust of the public it is meant to serve. This visionary project will inevitably spark a wide spectrum of reactions, a fascinating tapestry of excitement, skepticism, and everything in between. For many, the concept will be a thrilling symbol of human ambition and progress, a tangible step toward a multi-planetary future that promises to safeguard our most precious knowledge from any catastrophe. This perspective sees the vault not as an expense, but as the ultimate insurance policy for civilization, a profound declaration that our story is worth preserving against all odds. The sheer audacity of storing data on the moon captures a sense of wonder, appealing to our innate desire to explore and leave a legacy that echoes through the ages. Conversely, a significant and perfectly valid viewpoint will question the staggering cost and our priorities as a species. Skeptics will understandably ask why we are investing billions in a project off-world when so many pressing challenges, climate change, poverty, disease, and crumbling infrastructure demand resources and attention right here on Earth. This isn't a rejection of science or progress, but a heartfelt plea for pragmatic problem-solving. They might argue it represents a form of escapism, a high-tech fantasy that distracts from solving difficult terrestrial problems. This perspective frames the vault as a luxury for a technologically elite class, disconnected from the immediate needs of the global population. Addressing these concerns isn't about dismissing them, It's about engaging in a sincere and transparent dialogue about the long-term value of such an endeavor. Bridging this divide requires a thoughtful and sustained campaign of educational outreach that moves beyond technical jargon to connect with people on a human level. The message cannot simply be about terabytes and transmission latency. It must be about resilience and remembrance. We need to illustrate the very real vulnerabilities of our current digital infrastructure to solar flares, cyber warfare, and natural disasters, making the case for an off-world backup not as a sci-fi luxury, but as a practical necessity for global security. Furthermore, we must emphasize the project's role as the ultimate act of cultural preservation. This is about ensuring that the languages, art, music, and stories that define us, the very essence of our humanity, are never lost, even if the worst should befall our planet. It's a message that resonates with our deepest instincts to protect our heritage for our children and grandchildren. Building a broad, lasting consensus will demand creative and inclusive engagement strategies. Imagine immersive documentary series that take viewers on a virtual journey to these shadowed craters, making the abstract concept feel tangible and real. Interactive online platforms could allow people to virtually add a digital artifact, a family recipe, a recording of a folk song, a scanned drawing, to a symbolic time capsule, giving them a personal stake in the mission's goal of preservation. Collaborations with artists, musicians, and filmmakers can help translate the technical vision into powerful emotional narratives that stir the soul. The aim is to transform the Lunar Data Vault from a distant government or corporate project into a shared human achievement, a collective endeavor that belongs to everyone. Ultimately, shaping public perception is about more than just funding. It's about building a foundation of social license for one of the most ambitious projects in human history. It requires listening to concerns, answering tough questions with honesty, and continually demonstrating the profound, long-term value of protecting our collective digital memory. By fostering an open and ongoing conversation, we can move beyond debate and toward a shared vision, ensuring that this incredible step forward is taken with the understanding, the hope, and the blessing of the global community it is designed to protect. This vision of isolated data vaults operating in silent solitude is compelling, but it represents only one possible future. A far more dynamic and efficient model emerges when we consider these archives not as standalone outposts, but as integral components of a larger, living community on the Moon. The true potential of lunar data storage is unlocked through its synergy with future human colonies, creating a symbiotic relationship where each entity strengthens and sustains the other, weaving together to form the very fabric of a sustainable lunar economy. Imagine a bustling scientific outpost at the lunar South Pole, a habitat humming with activity. This colony itself will be a prodigious generator of priceless data. Its scientists will conduct unique experiments in low gravity. Its geologists will analyze core samples that hold the history of the solar system, and its life support systems will generate continuous streams of information on closed-loop agriculture and human physiology in space. All of this data is irreplaceable and critically important. Rather than building its own separate, small-scale storage facility, the colony could leverage the massive, secure capacity of the neighboring lunar data vault. This turns the vault from a remote archive into the colony's own local, ultra-secure server farm, handling its daily data needs while simultaneously preserving a backup of its most vital information. The colony benefits from enterprise-level data security and longevity without having to develop the specialized technology itself, while the vault gains a primary local customer, justifying its presence and operational costs. This partnership extends far beyond just data services. the colony transforms from a mere client into an active operational and maintenance partner for the Vault. Those autonomous repair robots we discussed earlier, instead of being solely pre-programmed from Earth, they could be overseen and even directly controlled in complex situations by human technicians living just a few kilometers away in the colony. A colonist with engineering expertise could don a suit, take a short rover ride, and perform hands-on repairs or hardware upgrades that are too delicate or complex for even the most advanced autonomous systems. The colony's machine shops could fabricate custom replacement parts on demand using Lunar Regolith or recycled materials, creating a localized supply chain that eliminates the need and cost of shipping every single bolt and circuit board from Earth. This drastically reduces the Vault's downtime and maintenance complexity, making it more reliable and far cheaper to operate. The shared infrastructure benefits are where the synergy becomes truly powerful. Both the Vault and the colony require immense amounts of power. Instead of the Vault building its own independent solar arrays on distant peaks and the colony building its own separate set, they can collaborate on a shared, robust lunar power grid. They could co-invest in larger, more efficient solar farms or even a small nuclear fission reactor, creating a redundant and resilient energy network that powers both the habitat's life support and the Vault servers. This shared utility model eliminates wasteful duplication and ensures power stability for both critical operations. The same principle applies to transportation. The landing pads, refueling depots, and roadways built for the colony can be used to receive supply missions for the Vault. A single lander could bring fresh food for the colonists and a new batch of synthetic DNA storage for the archive, sharing the tremendous cost of each launch. Perhaps the most significant economic incentive is the way a data vault can help a fledgling colony become financially self-sufficient. In the early days, a lunar colony will be an enormous financial drain, reliant on continuous supplies and funding from Earth. The presence of a major, revenue-generating facility like a data vault changes that equation. The Vault attracts its own clientele, governments, global corporations, and scientific institutions who pay for the service of off-world storage. That revenue can be partially reinvested into the colony's development, funding new modules, better facilities, and more advanced research. The colony, in turn, provides the skilled workforce and physical infrastructure to support the Vault. This creates a virtuous economic cycle. The Vault provides a commercial reason for the colony to exist and grow, and the colony provides the practical means for the Vault to operate and expand. It transforms the entire endeavor from a purely scientific or preservationist mission into a viable commercial enterprise, one that paves the way for a broader, self-sustaining lunar economy where services and resources are traded locally, reducing dependence on Earth and solidifying humanity's permanent presence on another world. Charting a course for such an ambitious endeavor requires a clear-eyed view of the practical steps ahead, a roadmap that acknowledges both the incredible momentum of current spaceflight and the significant hurdles that remain. We can break this journey down into distinct, overlapping phases, each building upon the last to gradually transform this vision from a concept on a whiteboard into a functioning facility on the lunar surface. The first of these phases is already quietly underway, hidden within the broader objectives of ongoing lunar exploration programs. This initial scouting and validation period, stretching through the 2030s, will be dominated by robots, not humans. Missions like NASA, Commercial Lunar Payload Services, or CLPS, initiatives are the perfect vehicle for this early work. Imagine a small, commercial lander touching down on the rim of Shackleton crater. Its primary mission might be to search for water ice, but nestled among its suite of instruments could be a small, hardened experiment. This payload wouldn't be a full data server. It would be something far more fundamental, a test of the environmental conditions themselves. It might contain a series of sample materials, from specialized metals and polymers to experimental storage media like a sliver of 5-dimensional quartz or a vial of synthetic DNA, all meticulously monitored to see how they withstand the long-term effects of the deep vacuum, the extreme cold, and the radiation environment. Concurrently, rovers equipped with ground-penetrating radar will be meticulously mapping the subsurface, identifying the most stable and optimal locations for future excavation and construction. This phase is all about de-risking the entire concept, gathering the crucial ground truth data that engineers need to finalize their designs. Building on the knowledge gained from these scouts, the following decade, the 2040s, will see the transition from passive observation to active demonstration. This is when we move from experiments to prototypes. We can expect dedicated missions whose sole purpose is to deploy and operate a small-scale, but fully functional proof-of-concept data vault. This wouldn't be an exabyte-scale archive. It might be a single, refrigerator-sized module, perhaps launched as a secondary payload on a larger Artemis-related landing mission. This Pathfinder unit would perform a real-world shakedown of every critical system. It would land, and autonomous rovers would bury it under a layer of regolith. It would deploy a small power receiver to draw energy from a solar array on a nearby sunlit peak and establish a steady communication link with Earth. For a year or two, it would do one job and one job only: store a test dataset and continuously verify its integrity, all while relaying a constant stream of engineering data on its health and performance. The goal of this phase isn't capacity, it's confidence. Success here proves that the core technologies work in unison in the actual lunar environment, paving the way for investors and governments to commit to the much larger capital expenditure of a full-scale system. Assuming these demonstrations succeed, the 2050s emerge as the most likely era for the first true, operational lunar data vaults. This is when the vision becomes a reality. By this time, the foundational infrastructure around the lunar South Pole is expected to be far more developed. Reusable lunar landers, akin to SpaceX's Starship concept, should be making regular, affordable trips to and from the moon, dramatically bringing down the cost of transporting hardware. The first deployments will likely be modest, perhaps a cluster of a few modules storing a few petabytes of the world's most critical information, perhaps the backup of a global seed bank's genetic data, or the complete archives of a major international scientific collaboration like CERN. These early adopters will be entities for whom the value of permanent preservation outweighs the still significant cost. The operation will be largely autonomous, but it may be supported by the nascent human presence at a nearby lunar outpost, who could provide manual oversight for complex maintenance tasks that are beyond the capabilities of the robots. This period will be less about a single dramatic event and more about the steady, incremental growth of capacity and capability, one module at a time. The timeline, however, is not set in stone. It's a living forecast that breathes with the pace of innovation and investment. A breakthrough in launch vehicle reusability that cuts costs by another order of magnitude could accelerate the schedule significantly. Conversely, a major technical setback or a shift in global political priorities that leads to funding cuts could add years of delay. The single biggest accelerator will be collaboration. If the effort is embraced as a global priority, with space agencies, private aerospace companies, and the tech industry pooling resources and expertise, the 2050s target is highly feasible. This isn't distant speculation. The first steps are being taken right now. The rockets are being tested, the landing systems are being designed, and the storage technologies are being perfected in laboratories. The journey to securing our digital future on the moon isn't a story waiting to begin. It's a story whose first chapter is being written today in launch centers and research facilities around the world. This shift toward off-world data management would fundamentally reshape our relationship with information itself, creating a new, resilient layer to our global digital infrastructure. Imagine a future where the most critical datasets for human civilization aren't stored in a vulnerable facility in a specific country, but are distributed across multiple, secure sites on the moon. This creates a permanent, off-planet backup for our species, a concept that would inevitably spawn entirely new industries and services we can only begin to imagine. We could see the rise of specialized space-based archival firms, offering tiers of lunar storage for everything from national security secrets to priceless cultural artifacts. This wouldn't just be about storing data. It would be about guaranteeing its existence against any terrestrial threat, effectively creating a new market for existential risk mitigation on a planetary scale. The very economy of information would expand beyond Earth's atmosphere. This migration of our most valuable data would also catalyze the next great leap in networking technology, forcing the development of a truly interplanetary internet. The need for reliable, high-bandwidth communication between Earth and the Moon would accelerate advancements in laser communication systems, creating a backbone that could then be extended to Mars and beyond. The protocols and hardware developed for managing lunar data vaults would become the foundation for a solar system-wide web, enabling future colonies to remain seamlessly connected to the vast knowledge base of humanity. This isn't just an incremental improvement, it's the prerequisite for a connected, multi-planetary society, with the humble data vault acting as the critical first node in a network that will one day span the entire inner solar system. On a geopolitical level, the inherent nature of this endeavor promotes a powerful incentive for international cooperation rather than conflict. Building and maintaining such a complex system in the harsh lunar environment is a challenge so vast that no single nation can realistically undertake it alone for long. The sheer cost and technical burden will necessitate unprecedented collaboration, much like the International Space Station, but on an even grander scale. Countries that may be terrestrial adversaries would find themselves with a shared, monumental interest in the success and security of these off-world archives. This creates a powerful forcing function for peace, as any conflict on Earth that disrupts these collaborations would directly jeopardize access to humanity's collective backup, a risk no rational actor would be willing to take. The vaults become a powerful symbol of our shared fate. Perhaps the most profound implication, however, is psychological. The simple knowledge that a copy of our collective achievements, our art, science, history, and languages, is safely stored away from Earth could have a unifying effect on humanity's self-perception. It reframes our place in the universe from a single, fragile planet to a species that is taking deliberate steps to ensure its longevity. This act of preservation is a powerful declaration that our story is worth saving, a testament to the value we place on our own existence. It can foster a sense of global citizenship and common purpose, a much-needed counterbalance to the divisions that often define our current era. The lunar vault becomes more than a storage facility. It transforms into a beacon of hope and a symbol of our collective resilience. Ultimately, these facilities represent a pivotal moment in our technological and cultural evolution. They signal a transition from managing information for the present to stewarding it for the deep future, acknowledging our responsibility to the countless generations yet to come. This isn't merely a technical upgrade to our storage systems. It is a fundamental expansion of our horizon, both literally and figuratively. By placing our knowledge on another world, we are taking a crucial step toward becoming a truly spacefaring civilization, one that thinks not in terms of years or decades, but in centuries and millennia. The choices we make today in designing these first off-world archives will echo through history, shaping how future humanity understands its past and secures its future. And so we arrive at the heart of the matter, a vision that began in the profound darkness of lunar craters and culminates in the enduring light of human legacy. The moon's shadow zones present more than just a clever technical workaround. They offer a paradigm shift, a fundamental reimagining of how we approach one of our most pressing modern challenges. This isn't merely about finding more space for our digital clutter. It's about architecting a sanctuary for our collective soul, a place where the very essence of human knowledge and creativity can be insulated from the unpredictable tides of our own planet's future. It represents a convergence, a perfect storm of natural advantage and human ingenuity, where the universe provides the perfect conditions and we provide the will to use them. The journey to this point is a tapestry woven from countless threads of innovation. We've harnessed the awesome, timeless cold of these eternal nightscapes, a natural deep freeze that pauses the very processes of decay. We've learned to use the moon's own barren soil as a shield, turning a potential hazard into a protective barrier against the relentless rain of cosmic radiation. We've identified the ingenious synergy between the sun-bathed peaks of eternal light and their neighboring shadowed depths, creating a closed-loop system of power and preservation. And we are on the cusp of deploying storage technologies that feel like magic, encoding the sum of human literature into a speck of synthetic DNA, or etching entire libraries onto indestructible quartz crystals. Each of these pieces on its own is a marvel, but together they form a complete picture, a viable and breathtakingly elegant solution. Of course, the path forward is not without its obstacles. The financial barriers remain substantial, the engineering challenges are daunting, and the legal framework is still a complex web waiting to be untangled. These are real and significant hurdles that will demand our sustained focus, investment, and international cooperation. Yet, these are the kinds of challenges that humanity has proven time and again it can overcome when presented with a goal worthy of our collective effort. The same spirit that built the great libraries of antiquity and launched probes into interstellar space is more than capable of rising to this occasion. The momentum is already building with each robotic mission, each breakthrough in material science, and each new partnership between space agencies and tech giants, bringing this future from the realm of speculation closer to the realm of inevitability. What we are truly discussing here is the next chapter in the great human story of preservation. We have always sought ways to send our stories into the future, from the oral traditions of ancient cultures to the great printing presses of the Renaissance. In the digital age, our methods have changed, but our fundamental desire has not. We are a species that longs to be remembered, to add our verse to the ongoing poem of humanity. By looking to the moon, we are taking that ancient, deeply human impulse and elevating it to a celestial scale. We are ensuring that our digital footprint, for all its flaws and wonders, becomes a permanent part of the solar system's record. We are building a bridge across time, a promise to the future that our voice, in all its complexity and beauty, will not be silenced. The silent, waiting darkness of those lunar craters may soon become the most eloquent testament to our existence, a quiet whisper of everything we were, everything we learned, and everything we dreamed.